Okay, real quick, everybody close down your stuff for just a second. Look up here. This is a good one to go through as a group. Real quick. Okay, this is, yeah, I'll give you a little free help on one of the problems on here. Okay, so let's see what we got. A baseball player throws a ball straight into the air, right? This is, everyone I think is going to get a problem like this on the practice, what is it, the 2.7 practice, I think, right? The ball takes 2.6 seconds to return to its mitt. The ball was thrown with the speed of what? Okay, so let's identify. Let's just go through this one. And this is a great problem because depending on how you frame this question, you can do this in different ways, but they're all good ways. And I want you to see how they're consistent. When you start to see this, things start to fall into place. So what's given to us? Time. Okay, time equals 2.60 standard units. Acceleration is given to us. What's the acceleration? Negative 9.8, right? Negative 9.80 standard units. What else? Anything else? Okay, that's it, I guess, right? Okay, so there's a couple ways we could look at this. If we choose to look at this for the full trip, there is something else that's implied by this. What did we say the other day about if I throw a ball up in the air and it comes back down? Let's think about this now. If I were to take a videotape of me throwing a ball up in the air and catching it, would you know any different if I was showing you the actual videotape of the ball going up and coming down as compared to, let's say, what if I only filmed the trip up, but then I ran it in reverse for it to come back down? They'd look the same, wouldn't they? In other words, the upwards trip, or the downwards trip, let's say, is the exact reverse of the upwards trip, right? That's an interesting kind of symmetry. That's a time symmetry, right? We talked about maybe just a little bit how geometry, we talked about line symmetry and point symmetry. We talked about all this kinds of geometric symmetry, but in physics we can talk about time symmetry. That's really crucial. So if we have this time symmetry then, what can you tell me about the speed at which I throw the ball and catch the ball? They'd have to be the same, wouldn't they? Right? So if I consider the whole trip, then I could say that my final velocity, by the way, I'm looking for initial velocity, right? Everybody see that? So we're trying to find what's the initial velocity. How is the final velocity related to the initial velocity? They're the same, but their directions are different. So they're opposite. Same magnitudes, opposite directions, right? So V would equal negative V naught, right? So now what equation, we've got some information here. Why is that useful to us? If I can write V in terms of V naught, then that eliminates a variable, doesn't it? Right? Because I'm trying to solve for V naught. So that means where I used to have a V, I could trade it for a negative V naught. That variable's gone, right? That's good. Okay? So this counts as almost like it's an implied other piece of information that we have that's helpful, right? So for those variables, which equation would I probably use? 2, right? I'm using the one V equals V naught plus AT, right? We're trying to solve for V naught, right? But we could make the trade V equals negative V naught, right? So now I get negative V naught equals V naught plus AT. What would I do to isolate V naught? I've got some like terms, don't I? Everybody see that? Right? So I could just subtract V naught from both sides of the equation. What am I going to get over here then? Negative V naught plus negative V naught is? Negative 2 V naught equals AT. And then all I'd have to do is just divide each side by negative 2, right? And look what we did then. We end up with a pretty good equation. We get V naught equals AT divided by negative 2. Well, let's plug and chug here. So A, you told me, is negative 9.8. T is 2.60. divided by -2. That's going to give me an answer, isn't it? Okay, what's the sign of the answer going to be?
Oh, positive.
Positive, right? Makes sense, because we threw it upwards, right? Okay, that's one way to do it. Anybody have a different way to do it? What'd you do, Richard?
Could you cut the time in half?
Ah, good. Yes, you could.
How long it takes when the velocity is 0?
Very good. Okay, we could also, we could do something like this. Great idea. I was hoping somebody would think of that. Okay, so we could say, sure, the time is 2.6, but the time to get to the top is only half of the time it takes to go up and down because of our time symmetry, right? So let's call that, how about t sub 1/2, right? The time it takes to go halfway, just up to the top, would equal half of that, which is what? 1.30 seconds, standard units. Okay, at the top, if we're just going to consider half the trip, then for that journey, the final velocity, and here's the key, the final velocity is what? If we're only considering, now the trip we're considering is just when the ball goes up to the top. And then what's the velocity at the very top? 0, right? Because that's when it's going to come back down. So V is 0, A is -9.80. We're trying to solve for V naught. Same equation, right? So we've got V equals V naught plus AT, right? So we know that in this case, the velocity is 0. So if I subtract AT to the other side, wouldn't I just get V naught equals -AT, right? So for us, that's going to equal -9.8 times 1.3. Same answer. Right? Cool way to do it. Right? Make sense? What did we do there? That's a great strategy because, like I talked about before, in physics, if we can, we always want to try to trade a hard problem for an easy problem with the same answer. Right? Okay. Back to it.